Network time protocol is a networking protocol for clock synchronization between computer systems over packet-switched, variable-latency data networks. In operation since before 1985, NTP is one of the oldest Internet protocols in use. NTP was originally designed by David L. Mills of the University of Delaware, who still develops and maintains it with a team of volunteers. NTP is intended to synchronize all participating computers to within a few milliseconds of coordinated universal time. It uses a modified version of Marzullo's algorithm to select accurate time servers and is designed to mitigate the effects of variable network latency. NTP can usually maintain time to within tens of milliseconds over the public Internet, and can achieve better than 1 millisecond accuracy in local area networks under ideal conditions. Asymmetric routes and network congestion can cause errors of 100 milliseconds or more. The protocol is usually described in terms of a client-server model, but can as easily be used in peer-to-peer relationships where both peers consider the other to be a potential time source. Implementations send and receive timestamps using the user datagram protocol on port number 123. They can also use broadcasting or multicasting, where clients passively listen to time updates after an initial round-trip calibrating exchange. NTP supplies a warning of any impending leap second adjustment, but no information about local time zones or daylight saving time is transmitted. As of June 2010, the current protocol is version 4, which is a proposed standard as documented in RFC 5905. It is backward compatible with version 3, specified in RFC 1305. Clock strata. NTP uses a hierarchical, semi-layered system of time sources. Each level of this hierarchy is termed a stratum, and is assigned a number starting with 0 at the top. The number represents the distance from the reference clock and is used to prevent cyclical dependencies in the hierarchy. Stratum is not always an indication of quality or reliability. It is common to find Stratum 3 time sources that are higher quality than other Stratum 2 time sources. Telecommunication systems use a different definition for clock strata. Stratum 0, these are high-precision timekeeping devices such as atomic clocks, GPS clocks or other radio clocks. They generate a very accurate pulse per second signal that triggers an interrupt and timestamp on a connected computer. Stratum 0 devices are also known as reference clocks. Stratum 1, these are computers whose system clocks are synchronized to within a few microseconds of their attached Stratum 0 devices. Stratum 1 servers may peer with other Stratum 1 servers for sanity checking and backup. They are also referred to as primary time servers. Stratum 2, these are computers that are synchronized over a network to Stratum 1 servers. Often a Stratum 2 computer will query several Stratum 1 servers. Stratum 2 computers may also peer with other Stratum 2 computers to provide more stable and robust time for all devices in the peer group. Stratum 3, these are computers that are synchronized to Stratum 2 servers. They employ exactly the same algorithms for peering and data sampling as Stratum 2, and can themselves act as servers for Stratum 4 computers, and so on. Only strata 0 to 15 are valid. Stratum 16 is used to indicate that a device is unsynchronized. The NTP algorithms on each computer interact to construct a Bellman-Ford shortest path spanning tree, to minimize the accumulated round-trip delay to the Stratum 1 servers for all the clients. Timestamps. The 64-bit timestamps used by NTP consist of a 32-bit part for seconds and a 32-bit part for fractional second, giving a time scale that rolls over every 232 seconds and a theoretical resolution of 2/32 seconds. NTP uses an epoch of January 1, 1900, so the first rollover will be in 2036. Future versions of NTP may extend the time representation to 128 bits, 64 bits for the second and 64 bits for the fractional second. The current NTP v4 format has support for era number and era offset, that when used properly should aid fixing date rollover issues. According to Mills, the 64-bit value for the fraction is enough to resolve the amount of time it takes a photon to pass an electron at the speed of light. The 64-bit second value is enough to provide unambiguous time representation until the universe goes dim. Clock synchronization algorithm. A typical NTP client will regularly poll 3 or more servers on diverse networks. To synchronize its clock with a remote server, the client must compute the round-trip delay time on the offset. The round-trip delay I is computed as where TO is the client's timestamp of the request packet transmission, T1 is the server's timestamp of the request packet reception, T2 is the server's timestamp of the response packet transmission, and T3 is the client's timestamp of the response packet reception. Therefore, T3ATO is the time elapsed on the client side between the emission of the request packet and the reception of the response packet, and T2AT1 is the time the server waited before sending the answer. The offset I is given by the calculated I and I are passed through filters and subjected to statistical analysis. Outliers are discarded and an estimate of time offset is derived from the best 3 remaining candidates. The clock frequency is then adjusted to gradually reduce the offset, creating a feedback loop. The synchronization is correct when both the incoming and outgoing routes between the client and the server have symmetrical nominal delay. If the routes do not have a common nominal delay, there will be a systematic bias of half the difference between the forward and backward travel times. Software implementations. Reference implementation. The NTP reference implementation, along with the protocol, has been continuously developed for over 20 years. Backwards compatibility has been maintained as new features have been added. It contains several sensitive algorithms, especially to discipline the clock, that can misbehave when synchronized to servers that use different algorithms. The software has been ported to almost every computing platform, including personal computers. It runs as a daemon called NTPD under Unix or as a service under Windows. Reference clocks are supported and their offsets are filtered and analyzed in the same way as remote servers, although they are usually polled more frequently. SNTP, a less complex implementation of NTP, using the same protocol but without requiring the storage of state over extended periods of time, is known as the Simple Network Time Protocol. It is used in some embedded devices and in applications where high accuracy timing is not required. Windows Time Service. All Microsoft Windows versions since Windows 2000 and Windows XP include the Windows Time Service, which has the ability to synchronize the computer clock to an NTP server. The W32 time service was originally implemented for the purpose of the Kerberos version 5 authentication protocol, which required time to be within not more than 5 minutes of the correct value. The version in Windows 2000 and Windows XP only implement simple NTP, and violate several aspects of the NTP version 3 standard. Beginning with Windows Server 2003 and Windows Vista, a compliant implementation of full NTP is included. Microsoft says that the W32 time service cannot reliably maintain sync time to the range of 1 to 2 seconds. If higher accuracy is desired, Microsoft recommends to use a different NTP implementation. Leap seconds. On the day of a leap second event, NTPD receives notification from either a configuration file, an attached reference clock or a remote server. Because of the requirement that time must appear to be monotonically increasing, a leap second is inserted with the sequence 23:59 and 59 seconds, 23:59 and 60 seconds, 0 o'clock. Although the clock is actually halted during the event, any processes that query the system time cause it to increase by a tiny amount, preserving the order of events. If it should ever become necessary, a leap second would be deleted by skipping 23:59 and 59 seconds. Security concerns. NTP servers are susceptible to man-in-the-middle attacks unless packets are cryptographically signed for authentication. The computational overhead involved can make this impractical on busy servers, particularly during denial-of-service attacks. Only a few security problems have been identified in the reference implementation of the NTP codebase in its 25-plus-year history. The protocol has been undergoing revision and review over its entire history. As of January 2011, There are no security revisions in the NTP specification and no reports at CERT. The current code base for the reference implementation has been undergoing security audits from several sources for several years now, and there are no known high-risk vulnerabilities in the current released software. Several NTP server misuse and abuse practices exist which cause damage or degradation to a network time protocol server. NTP has been used in distributed denial of service attacks. A small query is sent to an NTP server with the return address spoofed to be the target address. Similar to the DNS amplification attack, the server responds with a much larger reply that allows an attacker to substantially increase the amount of data being sent to the target. To avoid participating in an attack, servers can be configured to ignore external queries, or they can be upgraded to version 4.2.7p26 or later. See also: Allen variants, International Atomic Time, NITZ, OpenNTPD, NTPDEC, NTP Pool, Daytime, ICMP Timestamp, ICMP Timestamp Reply, Precision Time Protocol, Notes. References. Further reading: RFC 958, RFC 1059, RFC 1119, RFC 1305, RFC 1361, RFC 1769, RFC 2030, RFC 4330, RFC 5905, RFC 5906, RFC 5907, RFC 5908, External links, official website, IETF NTP Working Group, David Mills NTP Project Page, Time and NTP Paper, NTP Survey 2005, current NIST leap seconds file compatible with NTPD.